press a key, a number pops up. You press another key, then one more, and in less than a second, the answer is right there. You've probably done this thousands of times without ever stopping to wonder what actually happens between the moment your finger touches that key and the moment the screen lights up. It seems almost too simple to be interesting, doesn't it? It's just a calculator. We all learned how to use one back in primary school, but here's the thing. The process happening inside that small, flat device every time you hit a key is one of the most elegant ideas in the history of human thought. And once you see it, you can't unsee it. It all starts with an almost philosophical question. How do you teach a machine to count? I'm not talking about how to display numbers. That's the easy part. But how do you get it to truly understand what a number is? To add two together, to know that 3 plus 4 equals 7 and not 6 or 8. As humans, we learn this as children almost effortlessly, but a machine has no intuition. It has no memory of counting blocks on a rug as a kid. It only has electricity. And strangely enough, that turns out to be plenty. The foundation of everything a calculator does is something called the binary system. Instead of the 10 digits we use, 0 through 9, the binary system uses only 2, 0 and 1. That's it. Every number you've ever typed into a calculator exists inside the machine as a long sequence of zeros and ones. For example, the number 5 is 101 in binary. 13 is 1101. It looks nothing like what we're used to, but mathematically, it works exactly the same way. It's no accident that machines use binary. It aligns perfectly with the nature of electricity. A wire either carries a current or it doesn't. A tiny switch is either open or closed, on or off, 1 or 0. When you press the number 7, what you're actually doing is triggering a specific pattern of electrical signals representing 7 in binary and sending it deep into the machine. This is where it gets really interesting. The calculator doesn't just store those signals, it processes them. And it does this using something called logic gates. A logic gate is an almost ridiculously simple device. It takes two electrical inputs, applies a rule, and produces an output. There are a few different types. For example, an AND gate only sends a signal if both of its inputs are active. An OR gate, on the other hand, gives a signal if either input is active. That's the whole job. Input, rule, output. On their own, these gates don't do much. But when you bring thousands of them together, connecting one's output to another's input, layering them in complex structures, something remarkable happens. They can add, they can subtract, they can compare two numbers and tell you which one is larger. All of this is born from simple switches following simple rules. The logic gate arrangement that performs addition is called a half adder, and for more complex cases, a full adder. When you hit the plus key and then the equals sign, a cascade of these tiny circuits springs into action. Each one handles its own small piece of the puzzle and passes the result to the next. Everything happens in microseconds, faster than you can blink, even faster than a single neuron fires in your brain. Subtraction, multiplication, division, they all boil down to variations of this same basic process. Multiplication, for instance, is essentially a very fast and efficient way of doing repeated addition. Division works through a process of repeated subtraction and comparison. The calculator doesn't think about these operations the way you do. It doesn't conceptually understand what multiplication means. It just executes a precise sequence of logical steps millions of times per second, and the answer comes out the other end. Then there's the question of how the answer gets back to you. The result initially exists as a pattern of binary signals, a bunch of zeros and ones. This pattern is converted into a format the screen can use. In most basic calculators, the screen is made of segments, small bars that turn on and off in different combinations to form the shapes of digits. The machine knows exactly which segments need to be active for each number and makes it happen instantly. What's easy to miss in all of this is how physical it is. We usually think of computation as something abstract, like numbers moving through a mathematical void, but inside a calculator, every step has a physical reality. Real electrons moving through real circuits, switches that are truly opening and closing. The number 7 isn't a concept the machine holds in its mind. It's a specific arrangement of voltage states across a series of transistors. It is mathematics turned into electricity. Modern calculators contain millions of transistors packed onto a chip smaller than your fingernail. Each one is a switch. Each switch is part of a gate. Each gate is part of a circuit. And this entire structure, when electricity flows through it, performs calculations that would take a human hours to do by hand, all in the time it takes light to travel just a few meters. There is something quietly astonishing about this, not because it's magic, but because the opposite is true. Everything a calculator does has a reason, a physical cause, a logical step, and yet the result feels so effortless and instantaneous that it's as if the machine just knows. It knows nothing. It just follows the rules. Very simple rules, applied very fast in very large numbers. And this, somehow, becomes enough to do something that looks a lot like thinking. Next time you reach for a calculator, maybe for something you could solve yourself, but just don't feel like doing, take half a second. Not to appreciate it in some some grand philosophical way, but just to notice that there's something fascinating happening inside. Notice the thing that people spent lifetimes trying to understand, which we now carry in our pockets without a second thought. If you've ever taken something simple for granted and then found out it wasn't simple at all, that's exactly what Most Questions is here for. Subscribe, and let's keep looking closer.